In yesterday's class, we have seen how substitution reaction happens. A strong nucleophile will react a carbocation, carbon center, and then it substitutes, forming various molecules like alcohols or even halogenated compounds or several species we have seen. We have also looked at yesterday free radical kind of nucleophilic or addition. General addition we can have seen already, like by free radicals using peroxy radicals. We'll also, the last topic what we had discussed yesterday was nucleophilic addition by means of strong nucleophiles, like especially anionic. So what happens once you have some electron depolarization, like for example, like carbonyl kind of groups, where you have delta minus because of dipole moment, delta minus and delta plus. So this charged nucleophile will directly add to the partial carbon, positive charge carbon, especially it forms an alkoxide. Okay, so alkoxide means if you have ethanol, potassium ethoxide, something like that. Okay, so this ethoxide ion, if you start working up with an acid, you get corresponding alcohols. Okay, so even this part we have seen, especially this is for nucleophile is very strong, like charged species. Let's take what happens when the nucleophile is weak. Okay, so weaker nucleophiles where you need to activate them before being attacked with the substrate. So you have something like this. In this lone pair of electron will bind with acid catalyzed reactions. So what happens? You start creating a complex. This and you create a slight positive charge over this carbon center, and once the nucleophile lone pair of electrons where it is not charged will start interacting with this asymmetric carbon, which is slightly slightly positive in nature, and then you start getting this intermediate, and upon doing working up and also adding for example Lewis acids kind of things, you start ending up getting the corresponding conversion, for example alcohols or like that. So this happens especially in acidic conditions when you have weaker nucleophile. So we have taken example of stronger nucleophile, weaker nucleophile. All the time remember, whenever you have a nucleophile, either the charge will play an important role or the lone pair of electrons will be attacked or will be reacted towards the corresponding intermediates. So there are several examples of such nucleophiles like water, alcohol, and amines. I think these are very familiar because this do not possess any charge. Now, let us also give some examples so that you get a clearer tradition of this. How nucleophile addition reactions between hydrocyanide and carbonyl groups are being added. So you know that cyano bond is C triple bonded, and we have carbonyl ketone group. Okay, so what happens here, because of the charge it starts to add to the nucleophile, this nucleophile will be added to the carbon electrophile. You can see this, and there is a rearrangement of, you are doing in acidic conditions, so you start corresponding cyanohydrate, okay, cyano group and alcohol group. So this is a nucleophilic attack, okay? and it's an addition reaction. So this is aldehyde in general. In order to get nucleophilic addition with respect to alcohols, if you want to do in presence of acidic medium, you end up getting hemiacetols. So you are adding nucleophile to a substrate like this. Okay, it's just addition of the reaction. So nucleophile is being added or interacted with an electrophile. So these are one set of features, and you also have electrophilic addition reactions. So instead of a nucleophile like charged or neutral molecules with lone pair of electrons, you can also have electrophiles. Okay, so it is generally it is, you can consider electrophilic addition as a reverse of elimination. So addition is you're adding, elimination is you're removing certain bonds, which is our next topic. And so electrophile you're already aware of, it's a electron deficient species. So you can see this, if you have double bonds, you start adding to a electrophile, okay, so that it saturates, and then the nucleophile will be out, and this will rearrange because of the charges, and then uh, you start getting up electrophile addition reaction. Example, you can take propene kind of molecules, one propene or like that. When you add hydrogen bromide, you start getting two bromopropane or one bromopropane. Okay, so where what happens is you are basically saturating. Okay, I think many of you are aware of Markovnikov's rule, where uh, the negative part of the halogen goes to, or like for example, the negative part of hydrogen halides will go to the carbon having least number of carbon hydrogen atoms. So this will be more favorable as compared to this. So these are some general electrophilic addition reactions. And today's main topic, along with uh, it's an exhaustive or an extended topic. Okay, for your syllabus, you have very limited, but I would like to make you to understand several aspects in elimination reactions. Okay, so again, all of you pay attention for this. We are looking at elimination. The name itself indicates we are removing certain bonds of a molecule. So what happens if you have a saturated system, you are making it an unsaturated one. So elimination involves loss of elements from the substrate to form newer pi bonds. It's simple, because if in a saturated hydrocarbons, um, if you remove elements, obviously you are creating unsaturation, okay, to the product. And so if you remove certain elements, especially hydrohalides like this HX, this is called dehydrohalogenation, because you are removing halogen, you are removing hydrogen. So dehydrohalogenations. Okay. So this generally happens by beta elimination. So you might be wondering what is beta. So you can see a halogen is directly bonded to carbon. This is called alpha, or alpha substituted halogen. The next adjacent one, which is located next to the halogen uh, substituted carbon, is called beta carbon. Okay, so this is beta carbon. So beta hydro, this halogenation, what happens? You see by beta elimination. So hydrogen from this and halogen from this will be lost to form a double bond, you can see, and you get a corresponding like for example, leaving group along with hydrogen halide. So this is the general reactivity for elimination reactions. See, I want everyone to be aware of, yesterday what we saw, for a saturated molecule, we started to substitute. Now, for a saturated molecules, we are removing the bonds, which is a very opposite of substitution reactions. Now, what you have for your syllabus is, you should be aware of E1 and E2 reactions. Okay, the basic example you should be aware of, but you should be more understanding with respect to E2 mechanism. Okay, so let's understand one by one. Okay, so you, by now you must be aware that we are removing the saturated bonds to make unsaturated. So basically, you can have in the reaction which removes acid dehydrohalogenations from the organic starting material. So you can see here, this material you are removing hydrogen bromide. Okay, hydrogen from one, bromo compound from one, you get corresponding alkene, and you end up getting some byproducts because of the basic medium where you are doing, along with the loss of HBr. Then you can see that in cyclohexane, which is chloro substituted, you remove hydrogen and chlorine molecule, you started to get a cyclohexane molecule, which is a saturated one, only one double bond. Again, do remember we have discussed about this molecule in aromaticity. What is the hits of hydrogenation for one cyclohexane if you have one double bond? So these are something about elimination reactions. In elimination reactions, especially because you want to remove one halogen and one hydrogen, or in general, that two components should be removed in order to get a double bond. What you do is, generally, bases or alkalis are being employed. Okay, so which are like negatively charged, like hydroxide species or alkoxides. Okay, so these are the standard bases people use: sodium hydroxide, okay, potassium hydroxide, and like methoxides, ethoxides, or potassium tertiary butoxide. Okay, so these are the key materials where, see, you see the leaving group along with sodium can form very easily that halogen bonds or like that. So that is the reason you should have certain bases to drive the reaction, elimination reactions. Now, in these reactions also mechanisms, if you want to understand like different mechanisms in elimination like SN1, SN2, in the case of elimination reactions, we have E1 mechanism and E2 mechanism, which is bimolecular or unimolecular kind of elimination. So same, 2 means bimolecular, 1 means um, like unimolecular reactions. So now E1, E2, in both the cases you see elimination, like SN1, SN2, both you see substitution. But how? The important things are transition state and differ in timing of the bond cleavage and bond formation. These are the important aspects. They only alter the timings with respect to bond breaking and bond forming. So it is essentially same as SN1 and SN2, but we are removing the bonds. Now, you might be wondering, we are removing, but what about the transition state, carbocation formation? Okay, so in that case, both E2 and SN2, they have several common features along with E1 and SN1, because until the transition state, it is same. Later, whether you are removing the bonds or whether you are substituting the bonds, that makes elimination versus substitution. Okay, so you can see here. So you have this kind of some molecules. Okay, so where you are having the base which removes the beta carbon to form corresponding pi bonds. So these are generally called as beta elimination reactions. So many of you are already by now aware, directly bonded it is called alpha, the one adjacent to that it is called beta. So this part of hydrogen will be removed. Now, the most common mechanism for, if you want to explain hydrohalogen removal, is E2 mechanism. Okay. So all of you pay attention for this. This E2 mechanism, obviously 2 is there, it exhibits second order kinetics, where second order kinetics recap when you have a substrate along with a molecule like base. So it is entirely dependent on substrate along with base in the rate equation. Okay, so rate is dependent on the substrate along with the base. That is the reason why it is called bimolecular reaction. So in this case, like in similar to SN2 mechanism, bonds broken, formation will be all in single step. Okay? Same like SN2, it's not like formation of carbocation followed by that. Okay? Let's take an example. So E2 reaction generally they involve strong bases. Okay? So why? Because the strong base should remove weakly acidic hydrogen. Generally, the beta hydrogens are slightly acidic in nature. In order to remove that, the base should definitely bind to this corresponding to get this hydrogen should be gone along with bromine. So corresponding compound should be given like this, double bonds along with the substituents. Okay. Now, remember we have a bromo compound. So again, you must be wondering for SN1 mechanism, we should take such examples. But now, see here, we have some examples like this tertiary bromo compound with a base. So what happens? You start creating an intermediate. Unlike SN1, you start creating carbocation. Here, you have an intermediate where nucleophile attacks and bromine also deposits. So you see that hydrogen, bromine, all are there in the transition state. So that is the highest energy. Once this energy is passed, okay, so here CBr bonds, OH bonds are being formed, and once the transition state happens and the reaction progresses, you start getting, after elimination of water and hydrogen bromide, you get or like bromo compound, you start getting a double bonded system. So the important aspect is the intermediate state. Now, so the same example. So if you have isobutyl bromide, this example with potassium ethoxide. So what here you have seen is same. You have used a potassium hydroxide. Now you are using potassium ethoxide. And then what happens in this reaction, you know that you are going to remove hydrogen and bromine. So you are getting a double bond. So you end up getting isobutylene along with ethanol and potassium bromide. Okay. So for easier reference sake, we have put potassium plus and bromide minus. So you can see this is the intermediate or transition state. So here you start forming the bonds with the carbon along with bromine which is being there. So this is the important step which drives you to elimination reactions. Importantly, still as I told, many of you might be recollecting how it is similar to SN2. Okay. So in this case, the dependence of base is very important. So as I told, E2 has both substrate along with base dependence. Okay. So there are close parallels between these two. For example, how you identify the base and the leaving group, and also how the solvents affect the reaction. So very important aspect, the base will be there in the rate equation along with the substrate. So that is the reason you call a bimolecular reaction. So whenever, if you want to increase the rate of E2 reaction, you should increase the substrate along with base, obviously. Generally, when you have hydroxide group or alkoxide group, E2 reaction proceeds faster. Okay. So same like SN2. SN2 also should have a stronger nucleophile for SN2 as compared to SN1. SN1 even water molecule can do the job because you have a tertiary butanol, like tertiary butyl carbocation is formed. Here, slightly positive charges are formed. Now, let's understand like primary, secondary, and tertiary, which are the fastest. But if you compare SN1 to SN2 mechanisms, they are exactly opposite in reactivity because we have taken tertiary butyl group, which is SN1 example. But you see how beautifully SN2 and E2 mechanisms they differ and how the R groups will affect. So these are primary, secondary, and tertiary alkyl which are bonded to carbon groups. So you know that SN2 reaction will be very good, very highest activity in the case of mono or primary carbons. Whereas tertiary carbons, it is no reaction. It is more of SN1. But in E2 reaction, highest reactivity you can see for tertiary carbons, least reactivity for primary carbons. Okay, so it's a, you can see that even though there is a dependence of base and substrate, but the reactivity is opposite as that of SN2. Okay. So this is a very you might have understood by looking at the example itself. The example is self-explanatory, but see the contrasting features between SN2 and E2. Also, if you look at the reactivity, as I told you, we have a transition state where you are forming a alkoxide or halogen bond. So in this case, like what happens is you are partially forming the double bond because of charges destabilization. So this is essentially called as transition state stability. Okay? So if you, in loose terms, how can you understand this is, here the double bonds are partially formed. Once you have this situation, what happens? The stability of these double bonds with the functional groups, like whether it is alkyl groups or like that, will stabilize, and that drives the reaction. So that is the driving force for the E2 such reactions. So when we call this terminology like 2 plus, here, like, this thing that is referred as transition or intermediate state. So this is one important aspect you should be aware of. And if you look at, we are coming to a very important rule now, is if you increase the number of substituents like this, more R groups on the carbon and also the leaving groups, you start getting very, very stable alkenes with E2 reactions. For example, you can see tertiary alkyl halide reacts faster than primary alkyl halide. The best example I have already taken is tertiary butyl group, very fast reaction than primary. Same thing, you can see a primary bromobutane. Okay, so you get very unstable mono substituted alkane, but you start taking a tertiary, um, for example, methyl propane with the bromo substituent, you get a di-substituted, more stable alkene. Because do remember, we had just shown you a scheme where tertiary carbons are highest they show high reactivity, E2 reactivity as compared to that of primary ones. Now, also, let's understand it even more. As I told you, we are coming to an important rule. So here, you are aware that we are removing bonds and forming the bonds in single step. So you have something like this molecule, you have bromo and different colors we have given intentionally here. Please all of you pay attention. This, in presence of alkoxide in any base, you get a major product like this and a minor product like this. So what exactly are we talking about with respect to mechanisms? So these reactions are regioselective. So what exactly are regioselective? They form ZZF products. Okay. Now, this essentially brings us to ZZF rule. Okay. So the main reason I had given say ZZF is to make you to understand. You should not like you're not supposed to pronounce based on Z. It's ZZF rule, which essentially talks when you have alkyl halides with two or more beta carbons. Okay, if you have beta hydrogen, that you can eliminate, but if you have two places where it is hydrogens can be removed, then only one alkene product is formed, other one is formed if the reaction proceeds. If you get two products, then it is one is weakly substituted, or for example, it's a minor product, other one is a major product. So as I told you, only one product will be dominated, and yeah, and also this kind of situation is called Setzer rule. So you can see here you have iodo and methyl cyclohexane. This is the molecule, and you can see here you have several like beta 1, beta 2, and this beta uh, different beta carbons. If you make a nucleophile, what happens? You start to form halogen and hydrogen removed from this place. So halogen from this and hydrogen from this, because if I'm not showing anything, it is obvious it is having hydrogen. So you start getting a tri-substituted alkene as compared to a di-substituted alkene. So you might wonder, here one hydrogen can go from this methyl group and iodine molecule can go. This will be a minor product as compared to a major product like this. So these are the outcome of Setzer rule. Okay. Now let us take a few more examples so that your understanding will be more clear. In the case of Setzer rule, beta elimination should have uh, more double bonds. For example, 2-3 places you should have a beta carbon. Only then you can see. And also these are regioselective, where you get one constitutional isomer. Okay, you can have multiple, for example, cis trans or that kind of things, and also uh, which gives rise to regioselectivity. So you can see this um, for this methyl butane for a bromo substituted one. Okay, so you have beta positions different here. Either hydrogen can be gone from this or from here, along with halogen. So you get this product as minor, but when you remove the beta 2 carbon from here, okay, so this gives rise to a major product like this because of Setzer rule. So whenever you have multiple carbons, especially beta carbons, okay, so the preferred pathway will be more towards a major product where you look for beta 2 hydrogen which is being cleaved, okay, which essentially gives rise to the regioselectivity in the compounds, in the final products. So again, several examples you can see. If you look at dehydrohalogenation, for example, this bromophenyl ethyl benzene. So this is phenyl ethyl groups, benzene if you see, and if you put some sodium ethoxide and all, you get major product. Of course, trans is most favored. You can see hydrogen from here and bromine from here. Okay, so you lose, and accordingly we get the trans product dominant as compared to a cis. Again, steric conditions, stereoselectivity are very important towards the final reaction. Now, the important points which you should understand from Me2 reaction is it's a second order reaction. It's a single step where you get the transient step, base attack, and double bonds formation partial, and then cleavage. Then tertiary groups will drive the reaction faster as compared to primary ones, and stronger base will drive the reaction, and if you have better leaving group, faster will be the reaction. And again, that point which I didn't more discuss today is when you have aprotic solvents, the reaction is faster. Remember, we talked about the hydrogen bonds with the solvent system and so on in the SN2 mechanisms and so on. So same to that concept. If you have aprotic solvents, the reaction will be faster. Now, Let us take an example of dehydrohalogenation of this certain molecule, where you have carbon tertiary butyl with chlorine group with water. So in the first example, what we have seen, we have taken tertiary whatever bromo or leaving group with NaOH or alkoxide. Instead of that, let's take water. So same like SN1 mechanism, but here you yield, the product will be C double bond CH2 by removing halogen and one hydrogen. So this is generally termed as even. So even mechanism similar to SN1 mechanism, you only see rate which is dependent on substrate alone. So even this this even mechanism, it follows a two-step mechanism. So same like SN1, carbocation formation, then reaction with nucleophile. So here the bond with the leaving groups, it breaks first and then the pi bond is formed. So that is the reason it is called unimolecular reaction. So you can see this. I'm even giving for even mechanism, even though you don't have for your syllabus, just try to understand this. It's very simple thing. So for even reaction mechanism, it follows a two-step mechanism where you see that first you get the carbocation, same like SN1. Now the base, the nucleophile what you had, which is a neutral nucleophile, will be attacking this to form hydronium ion to result, because you want to remove this hydrogen also, because you are it's an elimination reaction, and then you end up getting a saturated an unsaturated carbon from a saturated one. So this is essentially first order reaction. Same like SN1, you form carbocation, which is the intermediate step. Okay, this intermediate will react with the base, or for example in this case water, to remove halogen, and so that you end up getting a unsaturated carbon. So here energy, y-axis, and reaction coordinate, I didn't mention here, it should be reaction coordinate on the x-axis. So same like even reaction mechanism, if you have more number of R groups, okay, with respect to the leaving group, the rate of a reaction will increase. So tertiary carbons will show highest even kind of reactions where carbocations are more stable. Now in this case there is a checkpoint. Okay, you might be wondering, in the last even E2 example also you have told tertiary carbocation is stable, but base differs. Base matters a lot. So if you have stronger base, you follow E2 reaction, weaker base, even reaction. As simple as that. Okay. So in both the cases, carbocations formation is very vital, but whether it is even or E2, how do you understand is from how the reaction drives. Okay, how the reaction passes through, we can understand from whether it's even or E2 reaction. Okay, now again, even reactions are regioselective. Okay, you can apply Setzeff rule for even, but whenever, why we apply Setzeff rule is whenever you have multiple carbons with the beta carbons, where to remove hydrogen. If you get that down, you can see hydrogen will not be removed from this as compared to this. It will be major product. Yeah? So Setzeff rule applies well for even reactions. So what is the take home message is, even reactions, they follow first order, and you involve here two steps. First step is carbocation formation, then after that you remove the halogen bonds accordingly. So here also more substituted halides will react faster, and you have bases like water and alcohol oxide, they will or will drive the reaction better. Okay, like alcohols, not alcohol oxide, alcohols. And so the only difference between E1 and E2 is the base selection. So better leaving groups, the faster the reaction is. And here, as contrast to that of E2 mechanism, you should have polar protic solvents and ionic intermediates, which will stabilize the uh, transition state. So you see how interesting, even though we take one example similar, how we can lead into different, just by base selection, we can go for E1 or E2. Okay, so just some important points before we close this elimination is E1, E2, both of them, they have bonds broken and bonds being formed. Double bond formed and bonds broken like halogen, hydrogen. One point is the leaving, especially in E1 reaction, the leaving group um, comes it comes off before the beta proton is removed, and then the reaction goes in two steps as compared to E2 reaction. Okay? And here it is one step. So E2 versus E1 is only one difference, one step versus two step. Now, you might be wondering, everything is fine. You are telling sometimes strong base will favor E2, weak base will favor E1. So, which essentially is strength of base is very important. Strong bases E2, weak bases E1. So, how do we compare finally? Is E2 mechanism a very common and useful mechanism because you use stronger base, and alkoxides or hydroxides are generally being used. Tertiary butyl group will be very dominant, and even mechanisms because uh, it is you get generally SN1. You see, for example, when the reaction converts, you get substitution reaction, elimination reactant products together. Okay, so that is the problem with even mechanism. And because of weak nucleophiles. See, whenever you have weak nucleophiles for tertiary butyl group, obviously it can even substitute or you can eliminate. So there is always a competition. Which one, whether I want to get the bonds should be eliminated or they should be added or they should be removed or substituted. Very important. You won't see this even mechanism for primary amines because there is no carbocation formation. It's only partial charges. So this, I think many of you are already clear from SN1 mechanism. Now, how do you know whether it is substitution or elimination, especially for SN1 or even reaction? So here, carbocation formation is same in both the cases. After that, whether it is eliminated or substituted, we should see. So let's see what happens with respect to the carbocation. So this is a carbocation form. The nucleophile can add, you get substitution. But here, a beta proton is being removed. So you get the eliminated product. Okay. Now, always as I told you, there is a competition, stiff competition between SN1 and E1. Okay, but this is not much pronounced in E2 reactions. Now, if you have good nucleophiles among all these four, whether which one will form? Good nucleophiles, which are weaker bases, they favor substitution over elimination. Okay, so for example, if you look at this iodo-bromo compounds, thiol kind of groups, cyano groups, or acetate groups, these bases will form a substitution. So you can see this molecule is there, bromoethane, and you want to substitute iodine. So you get a substituted product because this is a weaker base, iodine group. But you see when you have a stronger base like this. Okay, so where depending on the steric hindrance and also how the tetravalent carbon is stabilized. Okay, so what happens, you will get more of elimination reactions like this. Okay, and so in order to finally conclude, E1 versus E2 two-step first order reaction, you can have competition with SN1, SN2, and you can get, I mean, let us not so much discuss about the stereochemistry aspects in these E2 reactions, but we start getting more of trans kind of arrangement, more stable products, and Sedzef rule of, follows here, and in both the cases you end up getting unsaturated carbons. Okay? So um, you should also see how the molecule competes in terms of base or steric hindrances and at various physical conditions. Okay. So this is the end or the important points related to the elimination mechanisms. Okay. So is there any doubt to any of you regarding the? Is there any doubt? Or else I'll just give you one small problem. Okay, so where you can really see the conditions and then tell me whether it is SN1 or even which why it follows. You no need to tell why. At least you can tell the match the following like that. Okay, so is it clear, or you are stuck with some aspect in elimination reactions, or you'll wait for the handout to be posted, and then you will any queries can be later discussed.
Yes, sir. We will discuss later.
Okay, fine. Okay, so as I see, there are no queries. Let's again post the handout and we shall see. Now, please look at these molecules. I hope you can see this slide. Now, A to D, you have different bases. Okay, and which is SN1, which is SN2, and which is E1 or which is E2. So I want if people can work it out and tell me, or I think even by looking at this you can see. Yes. Anyone in the class would like to answer this? Yes. Yeah. Tell me. Any answers from anyone? So I don't think so. It's very tough, but please look at the reaction and tell whether it is SN1 or E1 or E2. I know that you must be preparing for your exam sometime in the um, at 10:50, but we'll just discuss one more small concept and then you can. I'll leave by 10:25 or something like that. Yeah, first you can answer this point. Anyone?
Is it the
SN2.
first one is SN2?
Which one? Which one is?
First one is SN2.
First one is SN2. Okay, and
Normal substitution. And C is SN1 because it's on a tertiary carbon.
okay, and okay, and the first one is SN2. You told no. A is SN2.
Yes, I'm not sure if that's the right answer.
Okay, okay, no problem, no problem. See, obvious, right? Whenever you see double bonds, that's all. It's elimination versus. It's very clear. It's not very tough, right?
B is even.
Yeah, which is B is even. Okay.
B.
Yes, yes, fine. Yeah, and obviously D is E2. Is it right? Adil, any other comments or anyone would like to give some more? Again, see, one point I would like to raise here. Look at the conditions. I didn't give many details, like for example, temperatures or what is the solvent system. Even more deeper details are not given. Still, you could make out. Again, these are not very strictly the reactions what to be exactly followed, but still, in any case, it's a decent try, I can say. So, if you might have told these things, I think you are right. So B is E1, A is SN2, C is SN1 reaction, and D is E2 reaction. Okay. So this
So,
again, yes,
which was the elimination that required a strong base? Like the, you said some elimination required a strong base, right?
yes,
So,
yes, yeah.
which
See,
one was that?
no, see, E2 will require strong base. E2, always E2. See, in the case, E2 requires strong base, whereas E1 doesn't require strong base.
So, like, is there a big difference between NaOH and KOH?
No, no, it is same. That's what I told you. You should not see that. Again, you should see the steric conditions. Steric conditions and other things. If you look at B versus D, here in the case of D, you have more of steric conditions which alters. You know that it is an elimination. Okay, and you cannot do this reaction in water, of course. So that is the reason whenever you have same conditions, the the driving force will be the steric and other, which is the transient state stabilization. That is a major thing which drives whether it's EU. Because in the case of B, it is very straightforward. Okay, B it was very straightforward, but D you should only look in the terms of like regioselectivity at the same time.
Steric
Uh,
hindrance.
yeah,
So,
that is.
tertiary carbon. Okay, okay.
Yes, yeah. Okay, so yeah, if there are no doubts, let us um, quickly discuss an important aspect on. Just give me one second. So, still 10:20 or 10:25 or something like that, we will discuss at an interesting topic, okay, which already we are now discussing the reactive organic chemistry. I hope you can see this slide now. Okay. So here we are already into reactive organic chemistry. So we started substitution reactions, we started elimination reactions, okay, and addition reactions and so on. You must be having a very basic understanding from structural representation, okay, like isomerism and so on. We came to a point where we try to remove the bonds and add something else. Okay, so that is very important aspect. Now, let's go to oxidation reduction reactions. Now, okay, I mean, I intentionally striked out some important oxidants and reducing agents. Do not get worried out because in your first semester, 2018, when the syllabus were changed, we even had these oxidizing agents. But now for your exam or for your syllabus, you have only potassium dichromate and potassium permanganate oxidizing agents, and reducing agents, lithium aluminum hydride, sodium borohydride. Okay. Now, okay, so this is your syllabus. What is there for your syllabus? We are looking at oxidation reduction, taking these examples. One example is sufficient. Okay. And later we have these parts, but that we'll discuss in our next class. Now, I would like to ask any of you, can you give some importance or what is generally oxidation reduction with respect to carbon? I think many of you are well versed with um, in lab bio oxidation for iron and like reduction for chromium. All those things you must be aware. But how different do you think it is with respect to carbon. Anyone in the class would like to give some general points regarding oxidation reduction? Anyone? Anyone in the class? Like what
You can
happens?
relate it to adding and removing hydrogen.
Adding and removing hydrogen to carbon is considered as oxidation reduction. Yes, you are right. And any other aspect? Any other important aspect do you think it is discussed? Yeah, what you raised the first point is true. Let's see what are the important things by which we can understand oxidation reduction chemistry of carbon. So, with reference to organic molecules, because oxidation, if you want to understand, where carbon atom gains bonds, especially what bonds it is gaining, more electronegative elements, preferably oxygen, you call it as oxidation. When the carbon atom gains less electronegative elements, um, typically hydrogen, then you call like reduction kind of features. So now, please look at an example. We have a methane, we have converted into carbon dioxide. You know that there is an oxidation process. So methane to carbon dioxide. Okay? So if you oxidized alkane, you get alcohol, and if you further oxidize aldehyde and further oxidize carboxylic acid, then final is CO2. Do the reverse process, add hydrogen. So to CO2, if you add hydrogen, you start getting C carbon, like just right, very small substituting carboxylic acid, aldehydes, alcohols, finally saturated carbons. Okay, so this is very simple, okay, which I think many of you are already aware of. You know, adding oxygen, removing oxygen, or adding hydrogen, removing hydrogen. Now, let us understand more deeper what is oxidation. For various organic chemistry reactions or oxidation reduction, you can generally do, for example, adding oxygen to the substrate like this. Ethylene oxide you can get. Removing hydrogen is also oxidation, and removing one electron. Okay? Loss of electrons is also called as oxidation. See, we have applied electrochemistry principles, general chemistry principles, in order to make it a radical formation versus removal hydrogen and oxidation. So these three you can consider as oxidation. The exact opposite, add hydrogen to saturate, remove oxygen, and add an electron. So this is an extreme. So either you can do this particular. So now I think many of your idea or approach of oxidation reduction in organic chemistry has broadened. Okay? I think it has gone to next level because it's not just only about hydrogen versus oxygen. This many options are there by which you can alter, you can oxidize or reduce. Now, how do you define oxidation and reduction of these molecules? So, loss of gain of electrons or increase in oxidation number or decrease in oxidation number. So, even that is also good, like increase in oxidation number is called oxidation. For example, Fe0 to Fe3 plus in pore Bay diagram and so on. Here you know that that is also called as oxidation. Decrease in oxidation number, okay, even that is also called as, so for example, H plus 2, H2. In terms of organic chemistry, gain of oxygen or loss of hydrogen, you call it as oxidation. Now, what about oxidation states, okay, and all those things? If you look at the functional groups of these molecules, you look at increasing oxidation state. So, for example, you are basically converting into various sequences like carbonyl groups are being converted into carboxylic acids, alcohols are converted into acids, like that. Now, please look at this example like methane all the way to CO2. Can someone tell me what is the oxidation states of carbon in carbon dioxide? What is the oxidation state? Anyone in the class? Like what will be the oxidation state of carbon in CO2?
+4.
Plus 4. And what about carbon in methane? Plus 4 is right, Swati. Yeah. In methane, what do you think the carbon?
-4.
Yes, minus 4. Okay, so now I hope you understood now why I asked this question. So you people have told plus 4 for this and minus 4 for this. So now these are in between. Let's take an example. So from here minus 4 to plus 4, you are seeing the increase in oxidation state. So how we, I mean, depending on, there are some variations and also there are a lot of improvements which were done by Cram, Pine, Hammond and all, where instead of calling oxidation state, they refer oxidation number. So how do you do generally is, if you in general generally calculate is -1 for hydrogen, 0 for carbon and +1 for electronegative elements. If you do this, you end up getting -4 oxidation state for methane, and for like ethanol or like methanol or like that, you get -2. So you can even see at one place you will be having 0. Okay, so such is the improvements done by various groups in order to give a value for increasing oxidation state. Now, till now, I didn't give any examples. For example, you have a primary alcohol. You want to make, you will be getting, you know that if you oxidize primary alcohol, you get carboxylic acid. You take a secondary alcohol, ketone, a very, very textbook example. Yes. So now, here you are breaking CH bonds and you are forming CO bonds in the same carbon. So you require stronger oxidants like potassium permanganate, chromic acid, or if you want to only stop at aldehyde, I don't know, you should, I want only aldehyde, I don't want carboxylic acid. There are some examples like pyridinium chlorochromate, okay, all this one and examples, which will reduce, which will oxidize to small extent, not higher, okay. So weak oxidants, they make into aldehydes, especially primary alcohols, secondary alkyls into ketones. And in any case, tertiary alkyl groups are not at all oxidized. Now, the very familiar example to many of you is, since you have probably seen in a lab or in the virtual lab sessions, potassium dichromate from chloride ion estimation or even potentiometer titration, you can see potassium dichromate is a very strong oxidizing agent. Okay, again, it's a very sensitive and dangerous material because it has chromium in hexavalent state. 6 oxidation state it is there, so it is very toxic as well. So this potassium dichromate, when you put it in acidified solutions, you get potassium is being dichromate ester is formed like this, and you end up getting this chromic acid. So please understand the terminologies, chromic acid and all. Generally it is used to clean the grease or dirt in some materials. Basically what you are doing is you are oxidizing the carbon, saturated carbons in the beakers or like that, and then you are cleaning it so that it is dissolved in water, and then you are throwing it out. Now, see, the main thing, probably you must be aware, in some places I use some different colors, and some places we use some different symbols or like colors or highlights to essentially show you how oxidation of a primary alcohol happens. So now we should only concentrate on this group. So if you take chromic acid, you get aldehyde. You leave the reaction for further, you get carboxylic acid. So how it happens is you don't have mechanism. I'm again telling you people, there is no mechanism for your syllabus, but just in order to feel for that, you get this approach by chromic acid, and you follow a chromate ester where you bond form repair happens, and finally you end up getting an aldehyde. Okay, so this is in general for like base abstraction, all those things. And some other examples you can see, you have uh, for example ketones. You end up, if you have that like oxidation, you end up getting acetic acid or like that. And you have, like for example, hydrogen, and you can see here a tertiary butyl group. You only get, in presence of potassium dichromate, a ketone. And if you take tertiary butanol group here as compared to this reaction, there is no reaction. Okay? So accordingly, we can keep the isomers, or you can see here also, you can see from like menthol, you can convert into methanol, okay, using oxidation, potassium or sodium dichromate as an oxidizing agent. Now, let us go for a mild, a friendly oxidizing agent, which is potassium permanganate. As far as I see, for your lab, there is no potassium permanganate based reactions, but it's a very interesting material where you can see manganese having 7 plus oxidation state. So here, in general, alkyl side chains of aromatic substrates are being oxidized. So you cannot apply this for methyl groups if you want to oxidize. And same like tertiary potassium dichromate, even tertiary alkyl groups will not be oxidized with this. So generally, it's a weak oxidizing agent than potassium dichromate, but still it's a very good oxidizing agent. Now you can see this potassium dichromate, sorry, potassium permanganate is used to oxidize carbons if they have weak bonds, like for example pi bonds, weak CH bonds, or even alcohols to aldehydes. And you also started to get uh, like for examples glycols, okay, and aromatic rings which are attached, all those things you can convert. So for example, you can see here you have like a aromatic ring, and you see here, and a ketone group is attached. So here, if you add potassium permanganate in acetonitrite and water mixture, you end up, you oxidize this to form OH. And you also have an 8-membered carbon, octane or octanoic acid. If you oxidize this, you start getting octanoic acid. So alcohol is converted into acid. Now, you cannot have over oxidation problem, same like potassium dichromate. Here, compared, as I told you, but compared to potassium dichromate, this is very safe and slightly weaker oxidizing agent. So you can see, you can even form a glycol, like like diols. So you have a double bond, add potassium permanganate, it forms this intermediate step, and then you end up getting like glycols. Okay? So this is also very important. So in this case, a cyclic manganese diester is important, which is driving towards diols formation. Okay, and very important point, we get here syn addition. So I am must be a bit surprised what is syn. It is towards the same side of carbon. Okay, syn addition or anti addition. Anti means now these are pointing in the same direction. This OH, this OH, and this carbon are in the same plane. You can have like if it is dotted arrows, then it is in opposite plane. Okay, so you can see you have take alkyl benzene and you get corresponding benzoic acid. And if you take tertiary butyl, there is no reaction. So one important point, how there is no reaction here and why there is no reaction, is you should have at least one hydrogen. Okay, one hydrogen should be attached to the carbon. Only then you can proceed to the oxidation reactions. Okay, so again, in the case of benzylic carbons and all, you don't have free this hydrogens, so that is the reason why you won't see any reaction. Now, okay, so probably I think we'll just discuss for 5 more minutes, and then I would like to you can prepare for your exam, and do remember both the batches should write the exam starting from 10:50. Okay, so exactly at 10:50 I will upload the questions, and please keep the video on, and then we'll do it. I will finish the exam, and only the last hour students who did not give viva, they can give viva on the last part of the class. Yeah. So I think there are only 4 students. Probably the marks are also being entered, so you must be seeing that. And so whoever it is absent, they can give the viva at the end of the 3rd hour end or 4th hour starting. Yeah. Okay. So let us give a basic definition about uh, instead of adding oxygen, what about hydrogen addition? So just a few aspects. Here, you must be aware of hydrogenation or nucleophilic reduction and so on. So you can see here, many of you are aware of this occlusion-based, catalyst-based hydrogenations, where you saturate a double bonded system in order to get this. So here also it follows a syn addition. So that is very important. At the same time, if you want to look at nucleophilic reduction, so you need to have some polarized substrate. And again, let us not so much worry about stereospecificity and how is the addition. And you can also have electrophilic reduction, like using sodium borohydride and so on. Okay, we'll not go for we'll not go more into the mechanistic details, but you can have electrophilic reduction or radical based reduction. Okay, using butyl lithium tin butyl tin. Now let us see the role of hydrogen. We have seen oxygen role in the form of dichromate and all, nascent oxygen and so on. Hydrogen as a reducing agent. So you are aware of this. Hydrogen can be in the form of hydrogen radicals or electrons, 2 electrons and 2 protons, and a hydride versus a proton. All these are hydrogen. Now, just see the reaction or a textbook example. You have platinum, palladium, or nickel. You want to add hydrogen. Okay. So essentially, you want to saturate butene to butane. So you want to add hydrogen here, make double bond into single bond. So you need to have the important role of catalyst. Same group with pentine. So a triple bonded system, you can saturate it by means of various catalysts. Now, I don't know how many of you are aware of Lindlar's catalyst. Can someone give me what is Lindlar's catalyst? Anyone in the class are aware of Lindlar's catalyst? Or in any case, if you are not aware, Probably in the next class you can check it and let me know. Okay. So here also for a unsaturated or a triply bonded system, you are making a saturated double bonded system. Okay. Again unsaturated but still double bonded system with cis conformation using Lindlard's catalyst. Now, how generally this happens? Okay. So you put sodium borohydride or whatever it is. So you have especially catalytically driven reactions. I mean, this is not there for your syllabus, but I just want you to understand what is happening. So you have a saturated, unsaturated bonds. You want to add hydrogen, you will get like this, or a triple bond, you get like this, okay, or something like this. So you have a catalyst support like metal, platinum, palladium, nickel. So you have metal surface. Hydrogen will occlude or it will form like nascent part of hydrogen which will bond to like metals like this, and then you add the substrates. So this will exactly confers or it will be attacked by the hydrogen, reactive hydrogen, and then once the reaction is over it passes. So this is the catalyst. So you can get stereo specific say, reaction, and also it's in addition because they are adding on the same side, so that the geometry, stereo specificity are retained. Again, the best examples for this reactions are sodium borohydride, lithium aluminum hydride. So there are several borohydrates like sodium, lithium, aluminum, zinc, okay, and cyanoborohydride and all. So all this borohydride means borohydride is BH4 minus. This borohydride will reduce aldehydes to ketones and corresponding alcohols. So it is the reverse of oxidation. Now, I think by now many of you are already aware. Lithium aluminum hydride or sodium borohydride, which one is stronger reducing agent? Okay, so which one is stronger reducing agent in this two? Anyone in the class?
Lithium aluminum hydride.
Lithium aluminum hydride is stronger reducing agent. Let us understand. And so it is like potassium dichromate with respect to the oxidation, where it oxidizes very fast. So in the case of hydride ion during this reaction mixture and all, how you understand this polar metal hydrogen bond in this cases is aluminum is less electronegative than boron. Okay, so you see that even though boron, aluminum are there in the same group, aluminum hydride bond is more polar. So which makes lithium aluminum hydride a very strong reducing agent. Okay, you cannot handle lithium aluminum hydride in air. You need to do in inert conditions like nitrogen atmosphere or passing oxygen at very minimal conditions. Whereas sodium borohydride you can operate, use them in air. Okay, in air or like normal conditions. So this is the reason why lithium aluminum hydride, the polarity of the bond gives rise to more stronger reducing capacity. Now let us take hydride ion, how it is being, it can reduce. So you have an aldehyde with sodium borohydride, you can form alcohols. Secondary alcohol you can get from ketone using sodium borohydride. And lithium aluminum hydride, as already you people are aware, it's a stronger reducing agent. So when you can use lithium aluminum hydride is when you are not able to reduce using sodium borohydride, or if it is non-reactive with respect to sodium borohydride, then you choose lithium aluminum hydride. Okay. So for example, this you have carboxylic acid, you can form corresponding primary alcohol. You have an ester, you get corresponding a primary alcohol. Okay. Where you cannot use sodium borohydride, because if you use sodium borohydride, you will be ending up getting a ketone. Okay. And here same like ketone or secondary alcohol as compared to this. So in order to get one attack, you can go for lithium aluminum hydride. And very important aspect, how you can get amines, okay, from this. So you have amide CONH2. If you use lithium aluminum hydride, you get primary amine, or if you have this CONCH3 secondary, and also tertiary amines. That's a wonderful thing with lithium aluminum hydride with small amounts of water. Okay, so again, you do not have mechanism for your information, but in any case, you understand how you have the nucleophilic attack. Okay, this is a nucleophile and you get a charged here, and this will be attacked here. Okay, and then you are protonating the alkoxide, and accordingly you get the corresponding alcohols or like that. So simply, if you want to tell, you have a double bond to you can see how it saturates, and then you add hydrogens to form corresponding alcohols. Okay, from ketone all the way till a secondary alcohol. In the case of sodium borohydride, you can selectively reduce aldehyde instead of a keto group. So, for example, like this. Okay, so you can in C double bond O is there, so you can selectively reduce this aspect. Same way, you can keep the double bonds intact, but you can you can reduce C double bond O here. Okay, so that is the highlight of lithium, sodium borohydride. If you take lithium aluminum hydride, everything will be reduced. Okay, so now the important take-home message is lithium aluminum hydride is very reactive, and sodium borohydride is weak, or compared to lithium aluminum hydride, it is weak, but very good selectivity it gives. Okay? So this is the graph showing reactivity versus selectivity. Selectivity means I want aldehyde group to be retained. I want double bonds should be preserved. I want to reduce only this. So that kind of things, if you want selectivity versus reactivity, sodium borohydride is very good. Again, you do not have this for your syllabus, but these are some other reducing agents. Okay, like diisobutyl aluminum hydride, or red aluminum, or vitride. So these are all some standard things which you can be also aware of, but you do not have this for syllabus. Only these two will be fine. So what you can expect for your exams based on this is one example. So give reactions based on lithium aluminum hydride, sodium borohydride. Each reaction one if you write few lines about that reducing agents, then it holds good. Yeah? You did not explain any mechanism and all. Only thing is the products. Okay, that is very important.
Sir, more selective arrow means in the previous slide.
Yeah, more selectivity, as I told you. If you, as I told, you want to stop. You don't want to carboxylic acid is there. You don't want to make it into a alcohol. You want to stop at aldehyde. That case, sodium borohydride is good. Okay, sodium borohydride is it's mildly weak as compared to lithium aluminum hydride. Even sodium borohydride is a very good reducing agent, but compared to lithium aluminum hydride, it is weak. So that is the reason selectivity you can get. And you can see this example, right? You can see this example where the double bonds, you are not saturating here. You want to only reduce this group. Okay. In that situations, you can go for sodium borohydride. But if you take lithium aluminum hydride, you will make OH, but it will be saturated. Okay. So that selectivity, if you want, you can use sodium borohydride. Same in the case of potassium permanganate as compared to dichromate. Okay, so you don't want over oxidation, opposite. So in this case, okay, in that situations you can go for particularly weak or user friendly agents like this. Yeah. Okay. So I hope it is clear, Swati. Yeah.
Yes.
Uh, And again, these reagents, I think already are out time up. So we can use different solvents, okay, and like I mean, these are all again not very much important. Uh, this is the process how by which you can do the reactions by neutralization, and all those things are needed. But let us not so much discuss about this. But if you're interested, of course, you can go through this. Any clarifications we can discuss. Yeah? And mostly um, we'll discuss in our next class again next reactions, and think about what will be the products for these reactions. Okay? So in with this we can end the class now, and I hope okay, are there any doubts? If if there are no doubts, prepare for your exam now, and I shall upload the handout today so that you can have a look about oxidation reduction and SN1, SN2, all, and even E1, E2 reaction mechanisms. Okay? And so I hope there is no doubts, and see you all by 10:50. Okay? So good luck with your exam. Prepare well. And also one point I forgot, like the video lectures who are supposed to make, prioritize that and do complete it before your exam starts. Okay. So already Swati had already finished. I'll be posting it shortly once all the students will give the YouTube links so that it will be posted in your GCR. Okay, then we will stop the class at this stage, and all of you join exactly at 10:50